Alright, so in this video we're going to be expanding some of the concepts we explored last time on integration, and we're going to look at functions such as sine of ax with respect to dx, and we're going to learn how to integrate this. So in the last video we discussed how integration is basically the opposite or the inverse operation of differentiation. So if you have a function x to the power of n and you integrate it, you will get the function x to the power of n plus 1 over n plus 1 plus some arbitrary constant c. And the reason we need to put a c at the end of every integrated function is because once you differentiate a constant, it becomes 0. So we don't know whether the original function actually contained a constant or not. So it is important to include it as an arbitrary unit in the function. And then if we had more information about the original function, then we can solve for that constant. But for the moment being, we're just going to leave it as that. And we also learned that you can perform integrations such as, let's say you want to find the integral of cosine of x with respect to dx. You know that this is just going to be sine x plus c, because once you differentiate sine of x, you get to cosine of x. And then you keep going back and forth like that. Now what happens when you have a more complicated function like this? You have a constant a in front of the x here, so obviously it cannot just be as simple as that. So what should we do? Well, first of all let's have a look at what we can do here. So let's try and integrate this. So what function differentiates into sine? We know that that's minus cos, so let's write minus cos ax for the sake of argument plus some constant c. Now let's see what happens when we differentiate this, and let's see if we get back to sine of ax. So if we differentiate this function, we're going to get sine ax. So we're actually going to get that. Oh, sorry, we get a positive here, not a minus. So we get a positive here, but we also need to multiply by the derivative of the inside, which is in this case a. So that's going to be the derivative of this. Now, do you notice anything missing here? Well, we're missing that a at the front. So this cannot be the integral of that. We need something else. So how can we fix this function such that we have the a at the front? Well, one technique we can use is multiply the integral by a over a, such that we can move one of the a's, the one at the numerator, into the integral like this. So if we move it into the integral, that implies that we need to erase it from the outside. So that's just going to be 1 over a. Because a over a, that just becomes 1. So this is just another way of writing it. So we know that this is actually going to differentiate into that. So we can leave it as it is, but we're going to multiply by this constant. So this is going to become minus 1 over a cosine of ax plus c. So this is how it works, and the same thing applies to when you are integrating cosine. You will have to divide by that constant that is on the inside multiplying x. Now, you might be thinking, well, what happens if we're given a function like this? Let's say you're given the function cosine of x squared dx. Your intuition might tell you, well, this should integrate into the following. We know that the integral of cosine is sine, so this is going to be sine x squared, and we just said that you need to divide this by whatever the derivative of the inside argument. So we would be compelled to actually perform this kind of operation and divide it by the derivative of the inside, which is 2x plus c. Now this is very wrong, and there's a reason why. Because if we differentiate this function, if you remember the laws of the quotient rule, you will notice that in order to perform this kind of operation, you actually need to differentiate both the bottom and the top. So in the end, what would you end up getting? Well, if you have the function f over g, we'll remember from the quotient rule, you're going to have g squared, and you're going to have g f prime minus g prime times f. So let's see what that's in this case. So g is 2x. So this is going to be 2x the derivative of this is going to be what? This is going to be 2x cosine of x squared minus g prime, which is just 2 times f sine x squared over g squared, which is going to be 4x squared. And we can also simplify this by just making that 4x squared here. So we can just make this 4x squared. And we can expand this in terms of the denominator, but in the end we will end up with a sum of trigonometric functions here. Now, is this the same as that? Clearly not. So this is why you can never do this kind of thing. This formula only works when you have x to the power of 1 in the argument. This only works when you have a constant times x. It doesn't work when you have an actual function of x. If you had something else like 1 over x, or let's say another function like sine of x inside the cosine, this would never work. In fact, it's very, very hard, and in most cases it is not possible to find an analytic solution to an integral like this. In order for us to be able to find the integral of this, we will need to have something else. So we will need to have something like the derivative of the inside outside as well. Because you might think, well, what if we just multiply this by x over x? So 2x over 2x. And then move the 2x inside. That's exactly the same thing we did before. We cannot do this kind of thing. You cannot multiply this by a function of x. You can only do that with constants as we did here. So this would not work. So for the moment, you need to just get used to the fact that for most integrals, you cannot find an analytic solution to it. So you can only deal with very simple ones like these ones. So just to show you another example of that, let's have ax plus b to the power of n dx. You might think, well, is this one of those cases that we cannot solve? Well, we actually can, because we have a function of x that is a linear function of x. So we're going to have ax plus b. We can simply treat this as a single variable to the power of n plus 1 over a times n plus 1. And the reason for that is, don't forget the constant c, of course. The reason for that is that if we differentiate this using the chain rule, this is going to come down and it is going to cancel out with this. So let's try and differentiate this. N plus 1, a, n plus 1. And this is going to become ax plus b to the power of n, because we're going to subtract 1 from the numerator. So this is going to cancel out with that. And then we're going to multiply this by the derivative of the inside, which is in this case just a. So this a is going to cancel out with that one. And in the end, what do you get? You get ax plus b to the power of n. And obviously the constant becomes 0 because we're differentiating. So this is the kind of stuff that you need to be doing. So if you get a function that you cannot differentiate back into this one, then you know that you did the integration wrong. But what happens when you have some other function to the power of n? So let's say you have a quadratic function of x inside that argument. So let's try x squared plus 1 to the power of n. Now you might think, well, what if we do this? What if we do x squared plus 1 to the power of n plus 1? And we're going to divide that by the derivative of the inside, which is 2x times n plus 1 plus c. Well, this is kind of the same formula, so that's what we're doing here. No, this is wrong as well. Never do this kind of thing. And the reason for that, once again, you can prove it through differentiation, is that this kind of function, you're going to use the chain rule. So if you try to differentiate this, let's say we want to differentiate this, we're going to have x squared plus 1 to the power of n. So n plus 1 over 2x n plus 1 times the derivative of the inside, which is going to be 2x. But we're forgetting something here. Hey, we have this function of 2x multiplying the n plus 1. So we cannot just use the chain rule. We have to use the quotient rule. And the quotient rule is g f of prime minus g prime f over g squared. So you can see right here that I was doing this thing wrong the whole time, because I thought, oh, maybe I can do this and this will cancel out and it will come out nicely to this. But that's a very common mistake that people make. So you need to make sure that you understand the fact that this is a function that has another function of x in the denominator. So you would have to use this rule to find the derivative. And in the end, you will never get back to this. So this is why this kind of formula only works for when you have an expression like this to the power of n. There are, however, some special cases in which you can find an analytic solution to a function, but in those cases you actually need to have a specific condition being met before you begin the integration. So in such cases you can have something like a function that is the derivative of another function that is also involved in the same function. In such a case, you can actually integrate this and get an analytic solution. And this method is called the method of substitution. This is something that we will explore in the next video. But there are certainly a few other rules of integration that you can apply just to manipulate things around and see if you can get an analytic solution. But the crucial thing to know is you have these basic standard integrals that you can find analytically using these formulas. But for most integrals that you might find in practice, you cannot actually find an analytic solution. And that's a very important thing, because with derivatives we know that we can find the derivative of almost any function without any trouble. Even with implicit functions we can find derivatives. But integration is a bit different. You would think it's an inverse operation of the differentiation, so there should be the same amount of possibilities as derivatives, but there aren't, and that's a very important remark to make. So in the next video we're going to be learning integration by substitution that looks at integrals of this kind.